Here's a fourth test I'm working on right now, infometrics for complementarity. How do you know, how do you know that you've got a really good teammate to go with teammate A? Well, the correct choice, of course, is a reduction in structural entropy production, which offers the group a chance to produce maximum entropy.
Excuse me, 3 minutes left.
I'm sorry?
3 minutes left.
3 minutes.
3 minutes.
Thank you. So that gets us down to a recent discovery, a Tribe 1 competition with Tribe 2. How do you know that Tribe 1 is winning in competition? That leads to the discovery of vulnerability theory. Here's how vulnerability theory works. If there's a trade-off between structural entropy production and a group's ability to produce maximum entropy, and if the perfect team is at least structural entropy and it's engaged in competition with another team and it's been wounded, that structural entropy production increases, which tells the competitor that it has hurt the first team. So that leads to a couple of nice predictions. Enforced cooperation in China leads to vulnerability in its need to steal technology. Lo and behold, that's exactly what Amazon does. And that leads to the conclusions. First, a perfect team operates at ground state. It has intelligence in its interactions. It is in a state of low emotion. It has least structural entropy, which implies team fitness, and it's ordered like a biocrystal, and that allows it to reach maximum entropy production. And it works like focusing a telescope. We're pretty sure that not everybody buys into this next argument, but static reports cannot capture individual dynamic skills, team fitness, performance, nor interdependence very well. Only competition can identify perfect and dysfunctional teams. Second, reducing interdependence weakens teams. Third, sub-additivity of interdependence implies that the best teams evolve. They're resilient to shock, but perfect teams are irreproducible, implies that the only way to select the best teams is by trial and error. And finally, my last comment, vulnerability theory implies that shocks harm those teams with lots of redundant personnel. And I published that in 2020. That's it. Thank you.
Thank you very much, Bill, for great presentation and meeting the time constraint. Maybe we have time for one question.
Sure. I don't know how to get the screen back up.
I may have a clarification question, actually. I have seen that you referred to Markowitz's portfolio theory, but it was not clear to me what you had to say about it. Is it possible to, you have time to tell us that?
Any questions? I know I went through it very fast and I apologize for that.
I'm sorry. No, I was just saying that I've seen in the slides that you were referring to Markowitz's portfolio theory, but Markowitz's portfolio theory, right?
I'm not sure I
It was
understand.
one in your slide, but I had no time to understand what you will do with that.
If you could write it out, I'll give you an answer.
Okay, we'll send you an email. No worries. Okay. Any quick question coming? Okay. Otherwise, that time is good to. So thank you, Bill. I guess it's good to go to the second talk. So Ellis is going to present his paper with Duncan on unfulfilled expectation and labor market interaction on the Infometrics approach. So stage to you, Ellis. Okay, thank you. Good. We see your slides.
You do. Thank you. And you can hear me okay?
Yes, absolutely.
Thanks. Okay, I'll try to keep this as short as possible. I think I've reduced it down to just a few slides. So this is joint work with Duncan Foley, extending a model that we developed and published in Entropy in 2017, where we detailed the quantile response statistical equilibrium framework for using method of maximum entropy to infer joint distributions when one of the dimensions of the joint distribution is unobserved, and we have dependencies on both sides of those conditional distributions. So we were looking at well, we developed that to model Smithian competition, where we were using observed profit rates and a theory of competition for that concerns the entry and exit decision of firms that equilibrates the profit rate distribution. And what we discovered is we can use the observable marginal distribution of profit rates to reconstruct the joint distribution, including the unobserved dimension of entry and exit behavior. So the idea was that we can extend this framework into a multiple agent framework where we have explicit interactions. And so we're looking at labor market interactions, whereas opposed to looking at, say, the entry and exit decisions of firms, we have a asymmetry in the quantile decisions, which is that workers can't hire themselves, and employers need workers to produce. And so we have two agents, and they interact probabilistically. And we thought, well, this would be a useful way of generalizing some of the insights from search theory, and also clarifying some of the ideas surrounding frictional versus involuntary unemployment. So let's see if this is working. Okay. So the labor market, which we're considering, is just a very simplified treatment. So we're going to follow Peter Doringer and Michael Piore's labor market model here as a shape-up economy. You might think of the shape-up economy as a Home Depot economy, where the interactions take place in continuous at step intervals, where there's some pool of unemployed workers, and for some iteration of time, employers can show up and hire some amount of those workers. And there needs to be some, offers have to be made, and offers need to be accepted. And we're going to assume that these are going to be conditionally dependent upon the wage. And our question is, how do we model decentralized labor market interactions between workers and employers, and how do these determine aggregate outcomes, in particular unemployment and the distribution of wages? So the first dimension of the model is to identify the dependency of worker and employer actions on the state variable, which is wages. So we're assuming agents are choosing an action from a finite set of actions with a certain payoff and a mixed strategy. And as we've shown in the earlier model, is if we simply assume that agents are boundedly rational, we can find the maximum entropy mixed strategy, which is just maximizing entropy constrained to a minimum expected payoff. This is akin to Herbert Simon's satisficing behavior. So what we end up with is the standard logic quantile response function here as a description of the conditional probability of the action A here on an outcome, where we're assuming actions are discrete. And in the simplest case we consider is just two actions. So this Gibbs distribution reduces to the logic quantile response function, where we get the action A and A bar as the sort of negation of that, or the alternative action, is then defined by the differences in the payoff functions. So we model workers in the shape-up economy as facing a quantile decision of to accept employment or to turn down employment conditional upon the wage. So we get a payoff for accepting employment, which is just going to be the wage omega, and not too important here, these other variables here, but we can express, say, any costs of employment as M here, and the payoff for not accepting or turning down employment is just going to be the worker's fallback position, we call Z here. So the difference in the payoffs we can represent here just as omega shifted by some variable mu. Mu is may kind of be thought of as a it's tempting to think of mu as the reservation wage in a standard labor model. It's actually, as we'll see, the indifference wage, and some conceptual differences that make it important to distinguish. So with these payoff functions, we get the workers' quantile response functions here as logit functions. And employers in the shape-up economy face similar quantile decisions, but there's, on the other side of the interaction, is to either offer employment or to not offer employment conditional upon the wage. And the payoff then for offering unemployment is going to be the difference between the marginal revenue product, R, and the wage that they have to pay minus any search costs or user costs or whatever. And then we have a fallback position here to make it symmetric. So we get a similar expression, but the inverse of the workers' payoff function here in terms of the difference of payoffs for a employer. So we get similar logistic functions. And that's one side of the labor market interaction model, which is that employer and workers' actions are conditionally dependent upon the wage. And there are a number of interactions, but such as employers offering and workers turning down employment, or the sort of non-meaningful ones, which is workers accept a job which is not offered. So there's only one real interaction here which produces a observable outcome, which is employment. And that we're calling tau as the transaction frequency, which is just the probability that an employer offers employment conditional on the wage, conditional upon a worker accepting that job. And so we can see this is just a picture here of the quantile response curves here for workers and employers. And this gray line is the transaction probabilities for a given wage. Now, the other dimension of this labor interaction model is that the actual actions of employment or unemployment are going to have perceptible effects on the wage. There's going to be a feedback. So the assumption of quantile responses and actions actually tends to induce strong correlations between the outcome and the actions. So for example, because workers are more likely to accept a job offered at a high wage, the quantile response effect will tend to produce a higher worker expected wage conditional on accepting than the worker expected wage conditional on rejecting an offer. So workers' actions and wages tend to be positively correlated. And because employers are more likely to offer jobs at lower wages, the quantile response effects are going to tend to produce a lower employer expected wage conditional on offering than the employer expected wage conditional on not making an offer. So the employer's actions and wages are going to be negatively correlated. And if we have no further constraints, then the maximum entropy program is going to maximize the differences of expected wages conditional upon actions for each agents. But in market interactions, these correlations are offset by the impact of the action on the outcome. So the outcome is conditionally dependent on the actions of each of the agents. So when a worker accepts a job offer, that tends to lower the wage for that job. And when a worker rejects an offer, it tends to raise the wage for that job. Similarly, when an employer offers a job, that's going to tend to raise the wage for that job. And when an employer refrains from making an offer, that's going to lower the wage for that job. So to reflect this feedback or the impact effect in a constrained maximum entropy framework, we limit the differences in workers' expected wages conditional on accepting and rejecting offers, and the parallel differences in employer expected wages conditional on offering and not offering. So the form that this takes, if we look at this, it's really just, we have an outcome, a continuous outcome here, which we're considering as the wage. And in both cases, we're considering these feedbacks move the wage relative to some market determined level alpha, which is common to both agents since they're interacting in the same market. So that allows just a affine transformation of omega, the wage here. So we're really just looking at the conditional expectation of an outcome conditional upon a binary variable here. So you could look at this and say, well, really just constraining a type of average treatment effect, if you want to look at it one way, for each individual, but it's not too strong of a constraint. It just identifies that there is some feedback of some minimum feedback of actions on the outcome. And when we plug in the quantile response functions, these can be expressed as hyperbolic tangent functions. So the maximum entropy program that we're interested in is to infer the joint distribution over wages and actions. So we maximize the joint entropy here subject to normalization and the feedback constraint. And the first order conditions actually are going to predict a wage distribution. So in this is just by decomposing the joint entropy into the marginal entropy of the wages plus the weighted conditional entropies of the actions, we can solve this problem for the marginal distribution of the wages. And what we get here is the entropy of the conditional distributions, the quantile response distributions, and these hyperbolic tangents. Now, T here is just what we call the behavioral temperature. So the idea of just noticeable differences that condition the actions of an individual. So this T here is in the same monetary units as the wages. It's going to define the sensitivity of workers to accepting or not accepting a job in monetary terms. Alpha is the market level. So the behavioral parameters are mu and T, and the market level parameters are alpha, which is the general location of the market, and S, which is the inverse of the Lagrange multiplier on the feedback constraint. So S defines a scale for the market, or a market temperature. And again, it's defined in the same units, same monetary units. And we can use a basic identity of the number of jobs in the economy and the labor force being comprised of filled jobs and vacant jobs and workers, employed workers and unemployed workers, to get an identity here to allow us to derive expressions for unemployment and job vacancies. So where we take P here as an exogenous probability of job separations, we can look at the change in unemployment as the flow in times the flow out, where we're looking here at the transaction probabilities times the actual number of filled jobs which are accepted, which is defined by the wage distribution. And so we can, and setting these equal to 0 in equilibrium, we can solve for the unemployment and the job vacancy rate and calculate those. And we see those depend both on the transaction frequencies and the wage distribution and the exogenous separation probability P. Okay, and this is the last slide I want to look at here, which is an interactive, which pulls all of these ideas together. So here what we're looking at is on the leftmost heat map here is the level of unemployment. And you can see for some fixed parameters here, we get the red curve, which is the marginal distribution of wages. This is a predicted distribution of wages, which is not degenerate, right? And we can look at the conditional wages, conditional on accepting and offering, which is these black curves. And the dashed red line is the average wage. And then in the right panel here, we're looking at the average wage, the transaction probabilities, and the quantile response functions. And what we're looking at here is what we might think of as frictional unemployment, because in this sense, we have a situation in which the average wage is actually corresponds to the intersection of these two quantile response curves, which we can kind of think of as quasi-labor supply and labor demand curves. This is a probability that at a given wage, a worker is going to accept a job, and that given wage, the employer is going to offer a job. And so in this scenario, the only thing that we observe in terms of unemployment is going to be frictional unemployment. And we have a frictional unemployment here of about 4.5%. And this would be consistent with the type of frictional unemployment that we might observe in a search theoretic model. And notice though, the way that I've just set the parameters in this toy example here, I've set as a depiction of what we might expect in a real market is we have mu C greater than mu W, which is to say there's some positive bid-ask spread between what employers are willing to offer and what the wage at which workers are going to be indifferent between taking a job and not. And in that situation, we might look at this as a type of equilibrium, where we have equilibrium unemployment as a frictional unemployment and no unfulfilled expectations and no what we might think of as involuntary unemployment frictional unemployment is necessarily going to be an equilibrium outcome in this model. But there seems to be some lack of consensus on what we would think of as involuntary unemployment. And what we're thinking here as involuntary unemployment is what happens when basically we force these temperatures down to zero. Is there going to be any unemployment that remains that's not frictional? And one other way we could look at this is whether or not there's unfulfilled expectations on the workers' part. Workers who would like to have a job but can't bid that wage down. So one thing we can do is to look at this.
At least 2 minutes left.
Great. So let's just quickly just shock this economy and see what happens. So if we assume there's a negative shock to the economy and it reduces the reservation bid for employers by 1/3, what happens is it's going to drive the average wage down. So I've left a sort of ghost there of the picture before the shock, so you can see what happens. The wage distribution becomes asymmetric due to unfulfilled expectations. And we see a sort of Keynesian interpretation of unemployment where the average wage here is no longer intersecting we're sort of off that intersection of the quantile response curves. And so we could think, well, what happens as the economy adjusts to this new shock? Let's say it's a permanent shock. We see that shock initially has a pretty strong effect on unemployment. It drove it up to about 6.2%. So if we think that in the long run that workers' expectations and the market itself is going to adapt to this situation, we might think that workers' reservation or their indifference bid also falls by about 1/3, and that the market adjusts by falling about 1/3. And here it reinstates what we might think of as a new natural rate of unemployment. But what's interesting about this situation is that it seems to indicate that in the long run, it's clear that in the short run, money is not neutral, but in the long run, after there's an adjustment to that negative shock, it seems there's also non-neutrality of money, because unemployment has reasserted itself at a higher level of about 5.5% at a new lower wage distribution. So in the Keynesian sense, we're now, the system is adjusted to a new long-run equilibrium with the lower average wage and a higher unemployment rate. I think what Friedman would expect for the natural rate of unemployment to reassert itself is that for some reason, the behavioral temperatures of the sensitivity of workers and employers to changes in wages would also fall. But we don't see that there's necessarily a good reason to see why that might happen. Leave it at that.
Okay, you're all set, Elise?
Yep.
Okay, thank you very much, just in time. I guess Amos at least has a question.
Yeah, just a fast comment. Very interesting, Alice. Just a comment on in your first model, you assumed bounded rationality. If I look at your constraints, it doesn't seem that it's needed. I mean, you just said that it's greater than some U minimum, but nobody knows where this U minimum came from. So I don't think you really need this assumption. It doesn't seem to be used. It's just a comment.
Well, I mean, otherwise we need some other closure on the quantum response functions. I mean, I'm not sure how it's not needed.
Well, you can have a less tough assumption in a way, because you have something that you call your minimum.
Yeah.
We have no clue where it's coming from.
Nope.
Exactly. So so you don't need to claim that it's coming from bounded rationality. It can come from this, that, you know, I want something above 0, for example. I want something above -1, but So you have to have a minimum, but I don't think that you need to put it within the bounded oceanography. I think it just makes it more general.
Okay.
Yeah.
Oh, that's a good point. Thanks, Almas.
Thank you. Robin, quick question.
Yeah, hi, Ellis and Duncan. Very nice, very interesting talk. I was wondering if there was anything specific about this being in a labor context. I mean, the way you described it, it seemed to me that this could apply to almost any kind of matching scenario. So, firms contracting with each other, or even in some kind of markets context.
You're absolutely right. I think our original motivation was just to try to get some clarification on what is unemployment and what is involuntary unemployment when we look at labor markets from a statistical sense, and say, and what we find is, in this example, we have consistency with other explanations, like the efficiency wage comes out of this as well. Just the positive probability that individuals may remain unemployed is a perfectly reasonable threat point. But no, I don't see any reason that I think it's easy to generalize this to like search theory to, but it's a little bit more endogenous because or general, because it also endogenizes those probabilities of transacting.
Okay, thank you, Alice. So I guess it's time to move now to give the stage to Ximeng. He's going to present his paper on maximum entropy distribution based on quantile group interval averages.
All right, can you see my screen?
Absolutely.
Okay,
Right.
great. Okay, thank you for having me here. This paper is about information recovery. And in particular, I am interested in answering this question, how to estimate a distribution based on average of a given number of intervals defined by some quantiles. Here is an example, a real example. This is a summarization of Brazil household income distribution published by a World Bank. So for each year, they divide a sample, which we don't get to see, into 10 equal or quantile intervals, and they report the average income of each quantile, of each decile. And the goal is to try to estimate the underlying distribution based on this very limited amount of information. Now, what makes this difficult is that very often they do not report those quantiles that actually define these intervals. Otherwise, the ME solution should be quite straightforward. It would be a piecewise exponential distribution. But without knowing those quantiles, it's much more difficult. And what we did in this paper is we managed to come up with a ME solution. And it turns out that if we fit those quantile based interval average into a entropy optimization problem, we get a density quantile function out of that. And once we have that quantity, we can infer other quantities of interest, such as the quantile function, the distribution, the density, the Lorentz curve, they can all be calculated from that density quantile function analytically. Well, there is actually a small literature on this. There are two existing approaches. One, we can of course do parametric estimation, try to maximize the likelihood of some plausible distributions. And we can also do non-parametric, try to basically fit smoother kernel-based or sprite-based smoother to the summary statistics. But there is a common difficulty here is that regardless of if we are doing parametric or non-parametric estimations, the specification of the model is difficult because the sample size is actually fixed. We typically only have 5 or 10 pieces of interval averages. In that sense, the usual large sample asymptotics does not apply. That does not provide any guidance about model specification. And that is why we turn to this ME framework. I think we are all very familiar with this general framework. So if we are given some moment conditions, one way to construct a distribution is to maximize this distribution subject to this integrated to one condition and a moment conditions in the form of G of K, if we have K moment conditions. And this is the ME solution. Those lambdas are the Lagrange multipliers associated with those moment conditions. And this ME solution has some very nice properties. First is maximally non-committal or conservative or least bias. And it is globally, numerically very nice in the sense that it has a unique global solution. If it exists, sometimes the moment conditions, they are not self-consistent. And what is particularly nice for our case is that it's free of tuning parameters. We take the moment conditions as given and we try to maximize this differential entropy. And these here are some examples. The most famous example obviously is the Gaussian distribution. If we know the first and second moments, we have Gaussian distribution for the random variable defined on the real line. And for positive random variables, if we know the mean, we have exponential distribution, and there are other examples. What is closely related to our case is actually the histogram, which is the frequency of intervals based on known boundaries, is indeed a ME solution. ME distribution, it has a very simple functional form. It's simply the piecewise uniform distribution on each known intervals, if we know the boundaries. So how do we deal with the case when we have interval averages, but we don't know those boundaries? Okay, it turns out that we need to transform the interval average a little bit. Suppose we have K intervals defined by boundaries. The average of each interval is linked or can be expressed as a function of quantile. Okay, if we take the case interval, if we integrate the quantile on that interval, and we normalize it by the frequency of that interval, we get the conditional mean of that particular interval. And for a reason that should be clear in the next slide, we make some transformation to this interval to cumulative interval averages. Basically, SK denotes the truncated or cumulative average up to probability P of K. Okay, and if we use change of variables, we can write it in terms of this piecewise integration of the derivative of this quantile function. This derivative of quantile function is indeed what is called the density quantile function. It links density to a quantile function. Okay, and you might wonder, why do we, on the surface, it looks like we are making the problem more difficult. But if you look at the differential entropy, because we don't know the X, those quantiles, we have to transform it into the frequency space or probability space. Okay, we transform the density function into this density quantile function. Then use a change of variable. It is actually, the entropy becomes log of the first order derivative of this quantile function. Okay. And once we make this transformation, we can now fit those cumulative interval average into this optimization, entropy optimization problem. And the solution takes this form. It is a piecewise parametric, inverse, reversal of parametric. And if we use some simple change of variables, you have this very nice piecewise polynomial form, a linear form. And we can establish the uniqueness and the existence of this solution. And once we have this maximum entropy density quantile function, we can infer other quantities such as quantile, distribution, density, or Lorentz curve. For example, the density function, the ME density function based on this optimization problem takes this particular form. So it is a piecewise exponential distribution function. But here we have this ME, we have to first infer this ME quantile from our optimization problem. Okay. Now, how about boundary conditions? Sometimes, even though we don't know those boundary, those interval quantiles, we know the boundary of the distribution. For example, for probabilities, we know X has to be between 0 and 1. It turns out, again, the range of boundary conditions can be incorporated as a moment condition for this density quantile function. Okay, so that is just another moment condition for this density quantile function. If we add it into the optimization problem, we have this augmented ME solution. So what is new here is this additional Lagrangian for this boundary condition. Now let me give you some examples. The first example, all the examples are based on 10 equally quantile intervals. The first example is a log normal distribution. Here I calculated the estimated the quantile function. Second is a CDF. Third is the dense one is the Lagrange, the Lorentz curve. The second example is a beta distribution. Okay, you can see that we recover the underlying density quite closely. Always the density is the most difficult to estimate. Other quantities are basically integrations of the density function. And this is the application to that earlier Brazil income distribution. We do it for each year. So on the left, we see the estimated density functions. On the right, we calculate the Gini index based on the estimated density. And I also plot the black line is the official Gini index for Brazil. So you can see that our estimated Gini index is extremely close to the estimated one, even though we only have 10 pieces of information for each year. Now, the last part, we would like to compare two partition methods, equal space versus equal quantile. We want to know which method is more informative. Now, we did a simple numerical exercise. We generate some random sample and we divide it into 10 equal space or 10 equal quantile intervals, and we estimate those ME estimator. For equal space, the ME estimator is simply the histogram. And for equal quantile intervals, we use the proposed density quantile ME estimator. Then we calculate the mean square error of the densities. Now, the first example is the exponential distribution. On the left, we plot the black line is the ME quantile estimator. The red dash one is the histogram. And the dash curve is the true distribution. So you can see that this equal quantile grouping is more informative. And that is confirmed by the MSE on the right. The MSE of this ME density quantile estimator is much smaller. Now, the second example is a log normal distribution. You can see the problem when the distribution is highly skewed, equal space grouping could mask the true feature of the distribution. And that is why we see this big gap between MSE. Okay, when we use equal space intervals, the MSE is substantially bigger. And the last example is the beta distribution. We use this as example of when we incorporate definite boundary conditions. So again, we can see that equal quantile interval is much more informative, and the proposed ME solution does a good job in terms of recovering or estimating the underlying distribution. Okay, I guess that's it.
Thank you so much, Siming, for Mother. You are perfectly in time, and your talk was very interesting. We have time for questions.
All right, let me stop the sharing. Oh, here.
Yes, maybe, yes.
Okay.
Any question?
There is a request for a paper for Jimin.
Oh, okay, I see it. Sure.
Is she's asking the paper too?
Yeah.
I see that. Okay. Okay. May I ask a very naive question? I'm sorry, because maybe it means I have missed what you do, because I found the topic very exciting, but it, of course, it's not your fault, but in 50 minutes it's hard to understand. Are you considering the bounds of your interval are non-parameters? This is a way to interpret what you do? To say, when I have to estimate this distribution, I have additional unknown parameters, which are the bounds of the interval.
So this question is for whom?
From Eric, sorry, from the chairman.
It's for you. It was a
Dimin,
question.
I am Eric Renault. I'm talking.
In your chair.
Okay, something wrong? I don't know.
Could
Jimmy,
be.
do you want Eric to repeat his question?
Oh, yes, please.
Okay, sorry. Okay, it has been a bit too fast for me, not your fault, of course. But I was not sure to understand the meaning of what you do. Are you seeing the bounds of your intervals as unknown parameters that have to be estimated in the process?
Well, trying to estimate a distribution based on average of those intervals.
Yes, I understand that. And I understand which is challenging is that you don't know the intervals.
Yeah, we don't know those bounds.
Okay, and so are you? I have no time to think about it. Are you estimating these bounds at the end of the day?
Oh, I'm not trying to explicitly estimate those bounds. I'm trying to estimate the entire density quantile function.
I understand.
Once we have the
Okay.
quantile function, we can infer those interval bounds from the estimated ME quantile,
Yeah,
density quantile function.
There's an
which
implied
is the
estimation.
derivative of the quantile.
Sure. No, sure. Okay. Yes.
And I have one question. So suppose, I mean, I know, I think it's a very nice paper, but and typically one uses, this density estimation based on the Shannon entropy, the Jane's entropy density for the, data unit data, the usual regular data. But suppose I have interval data, okay, instead of unit data, then can you define, I mean, this may be not exactly related to yours, but can you define the density, the entropy-based density?
Well, that's a very good question. I think the answer is affirmative, and it's probably going to be easier because in your case, the data are censored, but the sample size is much larger. We might have hundreds of thousands of observations instead of just 5 or 10.
Yes, it will be larger data, but the data is, suppose the incomes are in interval and Y is on the interval, or just only the income is in interval data. Then I want to know the density of the, the income. Then what you're saying is that it's possible to do and obtain the density of X if X is an interval.
Yeah, I understand your question.
Yeah.
Well,
Okay.
I have to think about it, but I think it's possible.
Okay, good.
Okay, thank you. I think Aman is thinking about the work of his colleague, right? Gloria Gonzalez.
Yeah. Even Amos and I have been doing some work on some of the interval data.
Okay.
So in that connection. Okay.
All right, thank you.
Okay.
One very general comment. Jimin mentioned that competing methods have tuning parameters. In a way, so does maximum entropy, because the number of moment conditions and which moment conditions can make a dramatic impact on what the maximum entropy distribution will be.
Yeah.
So those are like tuning parameters as well.
Uh-huh.
Not really, I see.
Not really.
I don't think so, because you can test the constraints, which the moments condition will enter as constraints. So those will be, subject to testing, chi-square or whatever you want. So it's different than tuning parameter that is decided a priori.
No, but you can cross-validate tuning parameters as well. The idea is there's a certain arbitrariness if once you fix it. And here, if you fix the number of moment conditions, which functionals you use for moment conditions, side conditions can make a big difference. You can produce any distribution you want by choosing which functional moment functions you want to use.
Of course, but you go in order, in a logical order, from minimum, and you increase, and you see where if new information comes in. So you're right, there is analogy, but I think a tuning parameter is a stronger concept.
It could well be. It could well be. It's just that there are sample-based decisions.
Okay, so I think we have a break scheduled now. Last question before the break. Okay, so I guess it's time for me to thank the three speakers. We did a very good job, and see you after the break. Okay, thank you all.
Thanks.
Thank you.
Thank you.